In this presentation, we will be discussing CPU scheduling in multiprocessor systems, which falls under the advanced operating system concepts. We will cover the essential topics of load balancing and processor affinity, explaining how these concepts are crucial for optimizing performance in systems with multiple processors. Let's begin with an overview of multiprocessor systems. These systems consist of multiple CPUs or cores that share memory and peripherals. This setup leads to increased processing power and overall throughput. However, it also requires specialized scheduling algorithms to manage the distribution of tasks across these processors. Multiprocessor systems introduce unique challenges, such as maintaining cache coherence and managing memory contention. The scheduling decisions we make significantly impact the overall performance of the system. Scheduling in multiprocessor systems comes with its own set of challenges. Firstly, there's the issue of cache coherence. When a process moves between processors, the cache data associated with that process becomes invalid, requiring expensive cache flush operations, increasing memory access latency, and impacting overall system performance. Secondly, non-uniform memory access, also known as NUMA, architectures introduce varying memory access times. Local memory access is faster than remote access. Therefore, the placement of processes in memory affects performance, particularly for memory-intensive tasks. Thirdly, workload distribution is crucial. It's important to ensure that all processors have appropriate workloads. This involves avoiding situations where some processors are idle while others are overloaded. It also means handling varying task execution times and balancing system throughput with response time. Finally, process communication. Related processes often communicate frequently, and the communication overhead increases when these processes run on different CPUs. Synchronization becomes more complex, requiring a careful balance between communication costs and load distribution. Let's discuss load balancing in multiprocessor systems. Load balancing is the process of distributing computational workload across multiple processors. Its goals are to optimize resource utilization, maximize throughput, minimize response time, and avoid overload on any single processor. The main objectives of load balancing include maximizing system throughput and utilization, minimizing the average response time for tasks, preventing processor overloading or starvation, adapting to changing workload conditions, and balancing competing system objectives. There are several approaches to load balancing. First, static load balancing. In this approach, work is distributed at compile time, or system initialization based on predetermined metrics. The advantage of this approach is that it has low runtime overhead and predictable behavior. However, it cannot adapt to changes in workload and requires prior knowledge of the system. Next, dynamic load balancing. In this approach, work is distributed at runtime based on the current system state and processor loads. The advantages of dynamic load balancing are that it adapts to changing conditions and leads to better resource utilization. However, it introduces runtime overhead and a more complex implementation. Another approach is centralized load balancing, where a single scheduler makes all load balancing decisions for the entire system. The advantage of this approach is that it allows for global optimization and a simpler implementation. However, it presents a single point of failure and can become a potential bottleneck. Finally, the distributed approach, in which each processor makes its own load balancing decisions based on local information. The advantages of this approach are that it avoids a single point of failure and offers better scalability. However, it may lead to suboptimal decisions and introduces communication overhead. Now let's explore some common load balancing algorithms. First, round robin. This algorithm distributes tasks to processors in a circular order without considering the workload. It's simple to implement and provides a fair distribution of tasks, but it doesn't account for task complexity. Second, least connection. This algorithm assigns new tasks to the processor with the fewest active tasks, balancing the number of active tasks. It's better than round-robin for systems with varying task lengths, but it doesn't consider processor capabilities. Third, weighted load balancing. This algorithm assigns tasks based on predefined processor capabilities or weights, accounting for heterogeneous processors. It can be static or dynamic, but requires accurate weight assignments. Finally, work stealing. In this algorithm, idle processors steal tasks from busy processors' queues. This is adaptive to changing workloads and minimizes idle processor time, but there may be potential contention on queue access. Let's move on to processor affinity. Processor affinity refers to the binding of a process to a specific processor or set of processors, preventing the operating system from migrating the process to other processors. The benefits of processor affinity are that it improves cache performance by maintaining cache locality, reduces cache invalidation and cache misses, minimizes memory access latency in NUMA systems, provides predictable performance for time-critical applications, and reduces context switching overhead between processors. There are primarily two types of processor affinity, which are soft affinity and hard affinity. Let's start with soft affinity. In soft affinity, the operating system attempts to keep a process on the same processor, but may migrate it if necessary for load balancing. The characteristics of soft affinity are that the system can override affinity when needed, balances cache benefits with system load, is the default in most modern operating systems, and is more flexible for dynamic workloads. Next is hard affinity. In hard affinity, the process is strictly bound to the specified processors and cannot be migrated by the operating system. The characteristics of hard affinity are that it guarantees processor assignment, maximizes cache locality benefits, is useful for time-critical applications, and may cause load imbalance in the system. Balancing load balancing and processor affinity involves addressing a fundamental conflict, so let's consider that conflict. Load balancing aims to move processes between processors to distribute the workload, while processor affinity seeks to keep processes on the same processor to improve cache performance. Optimizing for one can negatively impact the other. The system performance depends on finding the right balance. Now, consider resolution strategies. First, processor sets. Group processors and restrict migrations within those sets. Second, a time-based approach. Enforce affinity for a period, then allow migration. Third, workload classification. Apply different policies based on the process type. Fourth, hierarchical scheduling. Consider the cache topology in migration decisions. Now let's look at some real-world applications and best practices. Some real-world applications of these concepts include high-performance computing clusters, database management systems, real-time systems and applications, and cloud computing environments. As a case study, the Linux scheduler is a good example. Linux uses the completely fair scheduler, also known as CFS, with processor affinity support. It balances load while respecting affinity through scheduling domains and groups. Some best practices to consider include using affinity for CPU-intensive and cache-sensitive workloads, allowing load balancing for input-output bound or short-lived processes, considering NUMA topology in multiprocessor scheduling, monitoring and adjusting policies based on system performance, and using thread pools with affinity for server applications. In summary, finding the right balance between load distribution and processor affinity is key to optimizing multiprocessor system performance. The best approach depends on workload characteristics and system architecture. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.